Okay, so welcome back to the second part of the afternoon session. And the first speaker is Giulia Grancini, and she's going to talk about 1 year stable perovskite solar cells by 2D, 3D interface engineering.
For the kind invitation and all the organizers, it's really a pleasure to be here. So I'm Giulia Grancini, working at the PFL in Sion. That is a new center that has been established a few years ago in this small city in the Canton Valais. It's quite beautiful, 1 hour from Lausanne. The mission of this institute is to create new sustainable energies for the near future, and in particular, I'm working on perovskite solar cells. We know that the perovskite solar cell has really boomed in the last years, and it has been something that is not comparable to any other existing photovoltaic technologies. But as we discussed a lot in this section, the stability is really the problem for the future commercialization of this technology. Stability in terms of the degradation of the material upon exposure to water, oxygen, but also accelerated by heat and UV light. This induced the collapse of the three-dimensional perovskite structure into a zero-dimensional phases. For instance, for the methyl ammonium lead iodide, this corresponds to a bleaching of the materials that goes from black to yellow. So the aim of my work is to somehow combine efficiency and stability together to get an efficient and stable solar cell. In the last years, a lot of research has been focused trying to develop new strategies to get stable perovskite solar cells. For instance, this is an example on the use of cross-linking agent to improve the crystallization of the perovskite film and reducing the grain boundaries that are like gates for the penetration of water and oxygen. Other examples included the work of my colleagues at the PFL in Lausanne, which have used this very nice cation cascade, incorporating many different cations to stabilize the crystal structure of the perovskite. And more recently, there has been also a new family of perovskite that has been investigated. It's so-called bidimensional Rudelspotter perovskite phase, or quasi-two-dimensional perovskite phase, that has shown a much superior stability in terms of lifetime of the solar cells compared to the 3D perovskite, with efficiencies around 10%. So what is this family of low-dimensional or two-dimensional perovskite? You can think about our 3D perovskite, and you can ideally obtain your two-dimensional perovskite by slicing the 3D perovskites along the inorganic planes. In such a way, you can obtain isolated inorganic layers that are spaced by large organic molecules in the so-called form of two-dimensional perovskite. In this case, single inorganic layers are spaced by the organic cation, so n is equal to 1. Or you might also have a mixed structure where more than one layers are held together using a smaller cation here, like A, and combined with the larger cations, resulting into a so-called quasi-two-dimensional structure. This class of materials has really attracted an enormous interest because of the superior stability to moisture and to ambient conditions. Here an example of a solar cell showing 2D perovskite with respect to standard methyl ammonium lead iodide. However, they possess contrasting optoelectronic properties that are not really ideal for photovoltaics. For instance, they absorb in a narrower region. They show a strong exciton binding energy that can go up to 300 MeV, so you require extra energy to dissociate. Also higher trap density. So if we use it only 2D perovskite as a solar cell, you may not get efficiency more than 1%. On the other side, the quasi-dimensional perovskite have attracted more interest because of their tunability. Changing these two organic cations, you can change the band gap of the materials and also enhance the transport in the materials. So with within this class of materials, you can get efficiency over around 10–12%. Our approach was a little bit different. So the idea was to combine together these two different worlds, joining the 2D perovskite and the 3D perovskite together, in a synergic approach to take benefit from the enhanced efficiency of the 3D perovskite in terms of light absorption, charge transport, for instance, with the stability of the two-dimensional perovskite. So we used as three-dimensional perovskite the standard methyl ammonium lead iodide, and for the 2D perovskite an ammonium valeric acid-based materials, in order to get a new functional, stable, and efficient 3D 2D perovskite. How? The approach was very simple. We blended together the precursors of the 3D perovskite and the 2D perovskite together, and following a self-assembled process, we deposit our 2D, 3D composite on top of our mesoporous titanium substrate. Very interestingly, you can notice that upon blending these two materials together, the composite retains the individual optical and structural properties of the two phases. For instance, from the UV absorption, in black is the composite. You can see that the band edge is still at 780 nanometers, so it resembles the one of the 3D perovskites. But you can see also a band here that is due to the contribution of the 2D phases within the composite. You can also come to the same conclusion from the XRD, where you can see the diffraction pattern that give evidence of the 2D peak along with the peak of the methyl ammonium lead iodide. We blended these 2D, 3D materials together, and as I said, we deposited on a mesoporous titanium dioxide scaffold in order to characterize our material, and then with the aim to use it in mesoporous based solar cells. So first of all, we characterize the materials by simple photoluminescence spectroscopy in order to answer to this question: how is the segregation of these materials? How is the morphology of this 2D, 3D composite? And you can see that we basically excited from the bottom layer, and here is the photoluminescence spectrum of our blend compared to the one of the pristine two-dimensional perovskite. They match, while there is no emission if we excite from the top side. So these very simple measurements enable us to conclude that there is a kind of a vertically graded structure where the two-dimensional perovskite anchors mostly on the surface of the mesoporous titania through, for instance, carboxylid acid ending group, while the 3D perovskite is deposited on top, even if we deposit by a single-step deposition method. We can also further investigate this vertical phase segregation performing some micro-Raman analysis in depth, and you can see that measuring the signal from the top surface down to the bottom surface close to the titania surface, you can see that there is this peak that comes up that is related to the lead iodide bending mode and is particularly intense in the two-dimensional perovskite. So this gives you another confirmation of this vertical segregation of the materials. But importantly, it's also nice to observe that the two-dimensional perovskite and the three-dimensional perovskite, of course, at the, what's going on at the interface between these two materials? Is it a continuous phase, or what does it happen? And again, photoluminescence, simple photoluminescence spectroscopy can give us an answer. In these terms, we excited the material again from the bottom surface and from the top surface, and we explore now the more IR region, more red region, where we see the emission of the standard three-dimensional perovskite. And this is indeed what we observe from the top excitation. This is the classical, typical photoluminescence spectrum of our methyl ammonium lead iodide perovskite. However, if we excite from the bottom surface, you can see that the PL is really different. And this was extremely interesting for us, because you can see that there are two peaks in the photoluminescence spectrum. One that is matching with the standard emission peak at 780 nanometers, and another one appears that is more blue shifted. So it basically indicates that when the 2D, 3D perovskite forms on top of a mesoporous titania, the 2D perovskite is anchoring on top of the titanium oxide, but on the same time, it kind of templates the formation of a more ordered interface region that has a wider band gap. So it's still three-dimensional perovskite, but with a wider band gap, more ordered phases. So you can associate this interfacial region to still a three-dimensional perovskite, but more ordered, that has a slightly larger band gap. This has also been confirmed by some DFT calculations, where they show that at the interface, a perovskite phase with a slightly larger band gap is obtained. But of course, now the question here is how is the electron transfer among these layers? So a lot of investigation is ongoing, and I would like just to show you here a preliminary results. We are now working on this, try to understand how the charge dynamics happen within this interface. And for instance, here we compare the photobleaching at 760 nanometer with femtosecond transient absorption spectroscopy, where you can see that in the 2D, 3D composite, electron transfer is ensured in the picosecond time scale. I can give you more details about these ongoing measurements. Okay, now we take our materials and we wanted to see the effect of this blend into the device. So we used a different composition of the AVI of the 2D perovskite within the blend, and you can see that at an optimal concentration of 3%, we obtain for a mesoporous base configuration, so where the perovskite is sandwiched in between the titanium dioxide and the spiro, an efficiency of around 15%. What about the stability? Well, you can see that with the 2D, 3D blend, the stability was enhanced with respect to the pure methylammonium lead iodide. However, as has been reviewed by the previous presentation by Professor Hackfeld, still this architecture contains spiro and gold. So this is not really the optimal configuration in terms of stability. Spiro is not stable, gold can penetrate into spiro, so we know the effects of that. So we asked ourselves if we could replace this configuration with a more stable one. And we tried to use a different architecture that is much less explored in the field of perovskite, but we think is extremely interesting, and is based on the use of a carbon electrodes that replace both the spirometad and the top gold electrodes. Within this configuration, and without the use of two-dimensional perovskite, you can see that the stability is already better compared to the spirometad-based configurations. Now, with the use of our 2D, 3D blend, we obtain efficiency on a lab scale on the small cells of around 12%, and efficiency on a large module, that is 10 by 10 module, of around 11%. But more interestingly, we found that these kind of solar cells, so the 2D, 3D blend within the carbon architecture, really shows a very stable behavior with zero loss performances over many hours, more than 10,000 hours, leading us to obtain the world record for stability for this kind of solar cells. Work is ongoing, other open questions are there. How is the mechanism, the physics behind, the charge transport behind, the charge recombination behind? Many questions are still there that we are trying to address now. Inspired by this work, more recently, we are further working on engineering 2D, 3D perovskites together. And in this case, I would like just to mention to you a very recent work that was published last week that shows how to, again, take advantage of the use of two-dimensional perovskite, but in this case, it was a different approach. We used a layer-by-layer approach with a two-step method in order to get an in-situ layer-by-layer growth of a two-dimensional perovskite on top of a 3D one. Regarding the preparation and the technique to optimize this film, we took inspiration from previous work from my colleague Cho that used basically he wanted to get a graded 3D perovskite, in this case, where he used a different composition for the 3D perovskite. First, he deposited the standard 3D perovskite, but with an excess of lead iodide. And then the idea was a dynamic spin coating of an Fa material in IPA solution at an optimized mix concentration in such a way that the second kind of perovskite was naturally forming at the surface of the materials. So by taking inspiration from this previous work, we basically did the same, but we used as a second step the precursors for the two-dimensional materials. So the results was again the use, here is the materials that we use. This is the mixed perovskite that we use as the first layer. And then we use the organic PEA cation that we know forms a two-dimensional perovskite. So this is the result, and it shows you the absorption spectrum of the mixed composition and also of the pure PEA-based lead iodide materials that is organizing in a pure 2D perovskite. And from the XRD, you can see that the mixed, the layer-by-layer system in red shows the characteristic feature of the structure of the 2D perovskites. So again, we took our trick to measure the photoluminescence spectrum from the top surface and from the bottom surface. And you can see that from the top surface, you clearly see the emission from the 2D perovskite. So from the bottom, you can see that there is no emission here, while from the top surface, you can understand that we really had the formation of a thin layer of 2D perovskite on top, as also you can see from low-angle XRD. So we have a layer-by-layer structure with this thin layer of 2D perovskite on top that we believe is very important in enhancing two aspects. First of all, the structural stability of the material, but also the intrinsic character of stability in terms of water repellence. Indeed, we measured some contact angles, and you can see that with the addition of the 2D perovskite, the surface is more hydrophobic. So we believe that this is kind of one of the reasons of the better performance in terms of the stability of the materials that reflects in a better performance in terms of stability of the device. You can see here the red is the device, the layer-by-layer device. Efficiency as high as 20% have been obtained with a very nice stability that was improved with respect to the controller without the two-dimensional treatment. Note that these were done both in ambient environment without encapsulation, also compared with solar cell measurements in inert gas atmosphere. Just in the last 2 minutes, I would like to mention to you that our main research is on engineering this interface with two-dimensional perovskite and three-dimensional perovskite, but we are also working on engineering different cations and the optimization of the 3D perovskite. We know that the three-dimensional perovskite can exist itself because we can use only a small choice of organic cations, otherwise we disrupt the three-dimensional structure. However, maybe we are not completely sure that this cation cascade is really needed to get efficient and stable solar cell. Indeed, we are also working on simple configuration using only 10% of Fa in the mixer, and we got nice devices with, again, around 20% efficiency and good stability. And very recently, we have also worked with guanidinium solar cells that per se is too large to form a three-dimensional perovskite. Indeed, it forms a two-dimensional perovskite, but if used in a very small amount, like less than around 10%, it can infiltrate into the three-dimensional structure, preserving the integrity of the three-dimensional perovskite. And with this, you can see that, again, efficiency is around 19–20% with good stability. This was done in collaboration with the Cordoba University. So just to conclude, I think that tuning the perovskite dimensionality is a powerful tool to play with the material properties towards a stable perovskite, but the 2D perovskite alone is not enough. So interface engineering between 2D and 3D is a really interesting and promising route for device optimization in terms of efficiency and stability. We are very confident that this printable carbon-based technology can be a viable route for a marketable perovskite solar cell in the near future. This is ongoing research. Then we want to push to the limit the 2D, 3D engineering, so maybe 2D on the bottom and on top layer. Of course, a lot of attention has to be done in the interface energetics alignment in order to ensure the charge flow, the correct charge flow. Beyond photovoltaics, we are also working on some OLED and other LED and other kind of applications, and again trying to optimize our carbon-based technology. Let me thank my solar physics team. We are only 4 for the moment, but it's quite a nice group. And of course, Professor Naziruddin and all my colleagues at EPFL-SION. Collaboration and funding.
So thank you very much. We have time for 3 short questions.
I have 2 short questions of these 3. The first, what about EQE spectra for this 2D, 3D? And the second question is, do I understand correctly that you believe that there is additional charge separation on the interface between 2D and 3D?
Yes. Well, I start from the second. For the charge separation, I think it's happening, it's correct, because basically what we did, we measured the blend of 3D and 2D. We excited only the 3D, so we excite more in the red to avoid the excitation of the 2D, and we compared the photo bleaching of the 3D perovskite, with and without the 2D. So without the 2D, you can see the standard lifetime, hundreds of picoseconds in this case, was in the picosecond regime. When you put the 2D, this gets quenched. So now, the possible explanation is that you have electron transfer. Of course, what about charge trapping at interface? There are also other processes that can be behind, but we believe so. EQE, we measured the EQE. I didn't have the results here, but I'm happy to show it later if you want.
Thank you.
Saki. Oh, thank you. Very nice talk. With regard to the 2D, 3D composites or, layered structure,
yes.
I've seen in some of your PL spectra evidence for energy transfer from the 2D to 3D.
Excellent question. Thank you for the question, yes. Depends on the 2D perovskite that you put on top. You might also have some energy transfer. It's true. We are still investigating this because in this case, for instance, I think you are referring to this case.
Yeah,
yes.
Yeah.
So basically, in this case, we can see the emission from the 2D perovskite, but we are also exciting it because the excitation here was 450 nanometers.
Yeah.
Okay, so in this case, we are directly exciting the 2D perovskite, and this is the direct emission coming from that.
It depends on the penetration depth, obviously, the layered structure. But you can do separate structure on that by just looking at just depositing them on glass and just looking at one layer at a time or a mixture.
And we are also measuring the PLE, the excitation one that gives you the answer to that.
Yeah. Very good. Thank you.
Thank you very much. Very nice
Thank
talk.
you, Monica.
I really enjoyed it. I have thousands of questions, but I'm going to start for
We have the social
one.
dinner for that.
So you start working with AVA, that it has terminal groups amino and phosphonic,
Carboxylate.
right? But then you changed to another one that is amino-amino. Can you tell me why you choose that?
Yes. Okay, so in this case, we use this cation. One more. Sorry. This one. We used this one because we wanted to kind of induce a better interaction with the titania surface. And this also enhanced this vertical segregation that we get. So the 2D in this case is on the bottom. In the other case, we used the PEI because it was a simple choice because was one of the best candidate and most studied candidate to give you the 2D perovskites that was on the top. But we also use different one like butylamine cations or other cations that we synthesize in-house. So there is no specific reason for the choice of the PEA on top.
Okay.
In this case, yes, because we want to improve the interaction with the titania, but in the other case, no.
Okay, and the other question, last one, okay. Do we have time? Yeah, okay. It's very impressive, the stability of the solar cells.
Okay.
1 year with 10,000 hours.
Yes.
And I'm convinced that this zirconium oxide that you use has something to do with it.
Well,
There must be at the same time that you interact with titanium oxide, you interact with zirconium oxide also. I mean, the carboxylic part of the AVA. Do you know something about it? Can we be sure about this? Or?
Yes, well, you're right, this carbon cell has some speciality in this architecture because it's a very thick, it's 10 micron thick cells where you have titania, zirconia and carbon all printed, and then at the end you put the perovskite. So it's very different process with respect to standard mesoporous solar cells, and the most difficult part is the crystallization, controlling the crystallization. We will see maybe even in the next talk from Francesca. So the crystallization is the most difficult part. So to try to disentangle the effect of this 2D perovskite, what we did was study the 2D, 3D blend only on titania, only on zirconia, on different thicknesses, and comparing the PL spectra. So our conclusions are based on this detailed study.
But I guess the mesoporosity or the porosity of the layers matters a lot for crystallization.
Yes,
right?
and the thickness as well. Because it's a very slow crystallization. So you deposit the perovskite and then it's a very slow crystallization.
Okay. During coffee break.
Okay.
Thank you.
Sorry.
No coffee.
Thank you very much.
Thank you very much.